So, Sascha, the stage is yours.
Well, thank you, Marianne. Yeah, as I already said, working for many years together now. Today, well, thank you for having me, and I would like to show you some possible considerations for a proper simulation of fiber reinforced injection molded plastics. They are in a wide range used in certain industries, and there are certain effects that you can consider for your simulation. I will show you some solutions that you can use right away, or what you probably need additional software for. But our contribution to the open source community, for example, is that we provide such software to universities for free. So feel free to test it yourself. And so let's begin. But of course, beginning with a brief introduction of the company, for those of you that do not know us yet, Part Engineering is a company that, let's say, used to start with providing services in terms of simulation for companies that do not have any FEA department. And over the time, we developed some own solutions because we saw that there was a need for this on the market and there was no such solution available. So we had to develop it ourselves. So that's how we slightly turned from a service provider, a simulation service provider, to a software company. So nowadays we're doing, of course, both. And yeah, I'm with the company already for more than 16 years, and from the very beginning, working on the software products as well. Yeah, I'd like to show you what you can gain out of certain effects that come to your simulation when it comes down to injection molded plastics. But maybe first, since they are already displayed here, these are the 3 different software products that are available. This is Converse, Matscape, and S-Life. I will mention it during this presentation, but it is not a software presentation, of course. So just mentioning it where we have used which software. So main effect, of course, what comes to your mind when you think about fiber reinforced injection molded plastics is, of course, the fiber orientation. So this is something that can be very important to consider in the simulation because, of course, it has a huge effect on the material properties of such plastics. And if an injection molded plastic part is used in a way that, for example, a mechanical load is applied, then usually it is fiber reinforced because only then it can withstand, let's say, certain loads for industrial application. Maybe not the first thing that comes to your mind, but also, of course, very important, and everyone knows that works with injection molded plastics, are weld lines, of course, because these spots where the 2 melt fronts meet again can also be very crucial to your mechanical performance. And in the end, of course, also showing you how to consider this for a strength assessment of such parts. Yeah, as I already mentioned, starting with the fiber orientation, the effect of the fiber orientation is quite complex, but luckily the injection molding simulation, such as the animation on the left side shows, is able to predict the position and the direction of the fibers in such parts. So it is possible to take that into account. Usually they align in the direction of the flow, but of course not everywhere, and especially not if it's a very complex structure and the melt has to go around certain obstacles, then of course the orientation can be very different. So showing you this in a short overview, as you can see here, they tend to align in the direction of flow, but usually only in the outer layers of your part. So across the thickness of such a plastic part, you have highly aligned ones in the outer layers, while it is more random in the middle. And the middle, of course, can vary. That depends highly on the thickness of your part. Yeah, the thicker it is, the thicker is your core layer, because the outer layers pretty much stay the same. Yeah? And also it depends on the type of material. So, for example, if you're familiar with some plastics like polypropylene, of course, has a different kind of fiber orientation over the thickness than a polyamide, for example. So In a polyimide, typically you see a thinner core layer. And what does that affect? Well, quite obvious that, of course, with the fibers, the idea is to increase the stiffness and the strength of such a material. But you increase it different when you look down on what direction of loading is applied to such an orientation. So if we prepare out some test specimen out of a plate, inflow and cross-flow directions are pretty much in the direction of the melt flowing and cross to it, then you see a huge difference in terms of the stiffness and the strength. Probably you have seen that before when you're working with plastics. You can also see that in a stress strain effect of such a material, that you have typically a lower stress but higher strain when the load is applied across to the flow direction, while you have a higher stress but lower strain in the direction of flow, so where most of the fibers are pointing at. And you can think about it, it's quite logical. Yeah, the glass fibers, typically glass fibers, are way much more stiffer than a polymer, and therefore you have higher strain perpendicular to it, because then more, let's say, the polymer material, the matrix material is used than in the direction of flow where most of the fibers are pointing at. So coming to the first part, how to consider that. As I already mentioned, luckily injection molding solvers, such as, for example, in the Altair world, the Inspire mold, or with the APA, so the Altair Partner Alliance, also the partner software CAD mode can be used to predict such fiber orientation. And then there is possibilities such as ours, for example, to assign such orientation to your mesh. It can be either a radius mesh or, of course, also others like Alestaina you just mentioned. So there's different kinds of solvers the fibers can be assigned to. Pretty much all the solvers on the market are able to also consider fibers in terms of anisotropic material behavior. And yeah, this is what we provide with the software Converse, for example. And how to model a proper material model for that. You can go pretty much two different ways. First one would, of course, be the easiest in terms of in terms of material modeling, because then you just need two isotropic material models, but you have to mesh every fiber in your part, which of course is more likely to be for scientific research, but not for industrial applications, because you cannot measure all fibers in a industrial part. That would be a huge mesh, and would be way too many DOFs to solve. So instead, you can do the exact same thing by combining both, and then you have a homogenized material model that reacts actually the same as this fully meshed example, but is only one element. But what do you need to do to assign the material properties to that one element so it acts properly in terms of fiber orientation? There's quite a lot of material properties that you need to provide. So that's why typically a software is needed for that, to pretty much predict and then calibrate all the material properties needed. So for each and every element, the properties are different. I will come to that later, why it's not just one material model. And how to consider that in, for example, radius is you need to assign a local coordinate system to each and every element, because the fiber main direction in that element is always different, at least depending on the shape of your part. Of course, it's different. And second, you need to consider different material properties depending on the different directions for this anisotropic material model. You have different stiffnesses in the directions, different portions ratios, shear modeling, as well as, for example, in terms of taking temperature into account as well. You have different coefficients of thermal elongation. And if it's a nonlinear simulation, then of course you also have different stress strain behavior in the different directions. So 3 for the main directions and 3 for the shear layers. So coming back to why you need to have all kinds of different material models for your whole part, because we are talking about short fiber reinforced plastics, not such endless fibers or woven structures which you sometimes see in, for example, racing applications or all kinds of others, or the aerospace industry, of course. These short fibers, if you pick out one element out of your part, one little cube, then you not have just one fiber in it. You always have a certain distribution in it. And this distribution is always different depending on the position of your part, and even over the thickness, it is varying. So what you, for example, can have is all the way from a unidirectional one, where you have really all the fibers into one direction, like displayed here, all the way to a completely random one, where the fibers are completely random, and therefore, of course, this one reacts very different than this one. And you can have everything in between as well. Let's say something like that is a very general one, because usually you neither have a 100% oriented one, nor do you have a completely random one in your model. You always have a certain tendency. And this is displayed by the so-called orientation, degree of orientation. And what you can see here is that this pretty much says that most of your fibers are pointing in a certain direction, but you also have a certain percentage perpendicular to that, and then also a certain percentage in thickness direction. And that leads, of course, to a whole different nonlinear material behavior, if you look at this, and of course for different directions as well. So what's displayed here is always in the main direction and perpendicular to it. So for this blue, very general one, you have this stress-strain performance for in the main direction, if you make a tensile test, and this behavior would be perpendicular to it. And for the 100% one, of course, this would pretty much cover the whole range of the material itself, because there can't be anything higher than in 100% orientation, the stiffness and strength in this direction, if you load it in this direction, as well as there can't be any lower than this if you would put a load on such an element perpendicular to the main direction. Then, of course, it would be the weakest performance. Oops. So by considering that, now one is able to assign the different fiber directions, the distributions, and with the distributions also different anisotropic material behavior. And by doing that, it would be now possible to pretty much calibrate and see this effect for different directions when you prepare such a tensile specimen out of a plate, for example. And it's just impossible to cover that with an isotropic material behavior. And of course, that also not just works with static stress-strain behavior. It is also possible to apply this, let's say, whole concept for creep as well as strain rate dependency, because let's say the fibers or the anisotropy stays the same, no matter what speed you have by applying your load. And this is what our second software, for example, comes in for this Matscape. This is let's say a polymer material database where you can create material models for radius and other solvers, isotropic ones and anisotropic ones. There's already quite a lot of materials in there already, but it's also very easy to create one for your specific polymer, if you like. This is what it would look like if you consider this in radius. As Marian already said, we are very happy that they implemented this certain material model that was needed to consider the fiber orientation and to consider the anisotropy. Luckily, they even named it after our software, so it's Mat Converse. I think it's also Mat Law something, so it's also possible, but this is easier to catch. And depending on the degree of orientation, of course, you end up with different material properties in that card. Now you have the different stiffnesses listed here, and you have different so-called Hill-Yield ratios that are crucial for the anisotropic nonlinearity to consider. And then this refers to a reference stress-strain curve and scales it in a way that you get this effect of the different nonlinear material behavior for the different directions. Okay, coming from the fiber orientation to the weld lines now. Of course, weld lines can occur as well for unreinforced plastic parts, but they are, let's say, even worse if it's a fiber reinforced one. And typically, as I said, most plastic parts that face mechanical loads are fiber reinforced. So that's why this is probably the more important part. And if you're not familiar with the term of weld lines, I'd like to show you here how that happens to be created. The more complex a structure is, of course, you cannot avoid such weld lines because you always have certain spots in your part where the two melt fronts meet again. Either if it's just a screw hole or just a complex structure, but you cannot avoid them. So it's very important to investigate it. And if it happens to be in an area of your part where you have a very high load, then you probably need to reduce the strength in that area due to the fact that there is a weld line. This is, an additional effect that when you look at such a weld line, same thing here, by the way, injection molding solvers are able to predict weld lines as well. So the position of them and typically also an angle. The angle is important because if you imagine two melt fronts meet at 0 degrees, such as it would be here at the end of this filling process, where the two melt fronts really pretty much meet at 0 degrees, and then the filling stops. This one is, of course, even more critical than the one that happens down here because the angle is way much higher. And if you imagine two melt fronts meet under a certain angle instead of really frontal, then you can imagine that, of course, such weld lines are much worse than the ones at a certain angle. So the higher the angle, the less critical the weld line. So what we did in some research was we collected all available data from researchers from university and so on to, let's say, provide just a small software application, a sandbox or theory that you can use even without the software to have an idea of the strength reduction that you need to apply to such areas of your part. Of course, most of these tests have been done by simply injection mold tensile specimen with 2 gates and, of course, and the regular one, and compare these. So what you usually end up with is you have one without a weld line and one with a weld line. And what you can right away see is that pretty much the mechanical performance until the break of such a part is pretty much the same. So it is not really that a weld line is a problem to your part's stiffness. It is just, or can be a problem to your part's strength, so to the ultimate failure of your part. But of course, such researches only have been done, so to speak, about weld lines that occur when 2 melt fronts meet at 0 degrees. So there's not really some results that we can lay on under certain angles. So summing it up, this is also available on our website for free. You can check the results there, what this causes to certain materials. In terms of strength reduction, it's very easy to take that into account, of course, because you have nothing else to do than mark this certain area of a weld line and reduce the allowed strength there in your simulation. So, and it is provided as a factor, so you can easily apply that to your properties. And we were kind of surprised by the results on one hand, and then on the other hand, some of it is quite obvious. First of all, there's a huge difference between whether it is semi-crystalline or amorphous polymer. Those of you that work with polymers probably know the difference. And of course, there is a huge difference in terms of fiber orientation. Yeah, of course, that leads to the fact that the fiber orientation is very crucial to a weld line strength in such a way as if you increase the amount of fibers in your part, then of course this effect gets even worse because there's not much polymer material left, or at least there's less polymer material left. So the fibers become dominant in this part, and due to the fact that, let's say at this weld line spots where the two melt fronts meet and the polymer material does not combine in 100% anymore, if you have even less polymer material because of a high volume percentage of the fibers, it gets even worse. So it's, let's say, an easy effect to be considered by simply reducing the strength in that area with a certain factor, depending on the material that is used. So this is what a calculator looks like, where you can put the values in and calculate this factor. But you can also basically have a look at our research results and select your polymer material out of it yourself. And then you have a factor to be considered. Of course, the theory only provides reduction factors for 0-degree weld lines and not for all the other angles. This also can be mapped. And if you map it, you can even consider the different angles, of course. Yeah. So you have in one weld line, you need not have just one angle, but different ones. So if you want to really consider a varying factor, reduction factor, then you need to consider the different angles at the different weld lines. And therefore, of course, a mapping would be needed. So how does that affect, in terms of strength assessment, my prediction of my parts failing? So coming to one example that we had here, this was, let's say, it was an industrial application. It's a chain tensioner, automotive industry, but it was used to also test different weld lines and different fiber reinforced materials to, let's see, compare the different material models to the test results of such a part. It was quite an easy test. It was bounded on two sides and a load applied in the center, so expected to break in the middle at a certain point. It is, of course, possible to do all this without considering the fiber orientation, without considering the weld lines. But if you have very locally defined effects, then you probably need to take the fibers or the weld line positions into account. So this is what the fiber orientation for such a part looks like. You see with the different colors, the different fiber distributions. So again, you have some areas, especially on the outer surface, where you have a high percentage in a certain direction, and you also have some areas where you are, let's say, almost random. And considering that, it of course was way much easier to match the test results for such a part. Yeah, so what you can see here is the same part produced with different materials, different fiber percentages especially. So we have two different polyamides and two different fiber reinforcements, 35% and 50%. And yeah, when considering the fiber orientation, it is possible to match the test results in a way much easier way than you would match it with an isotropic material model, of course. Because only in this case, you are considering the real material properties. And since this is, let's say, the OpenRadioss Day, quite a scientific background, I need to at least put one equation on the slides. Yeah? What you can see here is the so-called Tsai-Hill failure criteria. So this can be used for the post-processing to consider the anisotropy in your failure model, because, of course, such things as equivalent strain, Mises, or Max principle do not apply anymore when it comes down to an anisotropic material behavior. So speaking of the same part, but where the intention was to create a really bad weld line in a certain spot, you can even see it here after production. So this was not after the test, so you have a visible, yeah, let's say, bad area in this part after the production of it, after it was injection molded. So in the filling simulation, of course, predicted that as well to be in this area. So once you do with the Tsai-Hill criteria, for example, and the anisotropy of fiber reinforcement in this part, you probably would still see on the downside of that part the maximum tie-heel strength. Yeah, and therefore you would probably predict to the part to fail there. But it didn't. So what we had to do in addition to that is apply what I have shown earlier, this strength reduction to the area where we have this bad weld line to reduce the allowed strength in that area. And then, of course, the result would rather look different, and therefore this area would be the more critical one, and we would have predicted the part to fail in the weld line. And then a second example provided by Essent, a material partner of ours, and what I have shown before in the animation with the weld line here. Of course, you could produce such a part without a weld line by putting the injection gate on top of here, but it was meant to be created, a weld line there, to figure out how the material performance is in a weld line. So same thing here, you can consider the fiber orientation all over the part, and you consider the different angles, if you like to, in this area where the weld line was created. And if you do that, of course, it is possible to figure out that this would be a weak spot for the part and even have some element deletion there and having the part cracking in the weld line. So if you are interested in more information about that, as I already mentioned, there is a lot more on our website to be found. Please enjoy visiting it and looking through some research that we did. I can assure you that this already gives you a better picture of how to consider this and already gives you some possibilities. If you need more than that, please, you're always free to talk to us to find a certain possibility to maybe test or use an application of ours to investigate on such parts further. Thank you very much for your attention.